What up, mathletes? Whoop, whoop. All right, let's do this. This is 12.3, solving quadratic equations by graphing. Your learning target is I will write quadratic equations and solve them by graphing. What? Okay, warm up. Look at this. Name the x-intercepts for each graph. Ready, set, go. And I'm assuming you paused it, as I do with all videos. So, again, I feel like I'm moving too fast. Just pause it. Move on with your bad self, and we'll get rolling. Okay? So, looking at this, guys, we have only one root right here, and that's at 2, 0. Boom, that's the x-intercept, right? We see right here we have 2. There's an x is negative 2, one that x is positive 2, so that would be at 2, 0, and negative 2, 0. Again, over here, just 1 right there is 0, so that's 0, 0. Right here we have just one x-intercept at, what is that, negative 1? So negative 1, 0. And right here we have none. It doesn't go through the x-axis at all, so none. Awesome. Well, okay, so we see quadratic equation. Go ahead and write that down. It's an equation that includes a quadratic expression. In other words, an x squared, right? Double root, two roots of a quadratic equation that are the same number. Awesome. Pause this, write it down, because we are going back to our regularly scheduled program. Solving quadratic equations by graphing. To write a quadratic equation related to a given function, replace y or f of x with 0. Okay? The solution of roots of an equation can be identified by finding the x-intercepts of the graph of the related function. So we're going to talk about finding roots. We're actually going to use factoring to do that in later lessons. But for right now, we're just talking about, hey, the concept is if I ever have something like f of x equals x squared minus 7x minus 8 equals 0, then what's the first thing I'm going to do is, minus 8, is I'm going to drop that f of x, and I'm going to say x squared minus 7x minus 8 equals 0. Kind of like I started right up there, right? And this is, by the way, no means related to any of these three graphs. It's related to this graph right here. I just wanted you guys to see what was going on. Okay, so look at these. What do we have? These are the types of solutions you will get with a quadratic equation. You'll either get two unique real solutions that cross the graph twice at two x-intercepts, one unique real solution, which is going to just hit the graph because it's either going to be a graph that opens up where the vertex touches it, or a graph that opens down where the vertex also just touches the x-axis in one spot. We're going to have ones that are shifted up and left or anywhere else that don't touch the x-axis at all, which means if it's above the x-axis, it has to open up. If it's below, it has to open down so it doesn't touch it ever. All right, so let's look down here. Use the graph of the related function to solve. We're just looking at this graph. Where does it hit right here? Boom. Right here and right here. And that is at halfway in between 0 and negative 2. So these roots are going to be negative 1 and 8. If we were to write them as intercepts, it would be negative 1, 0 and 8, 0. But if it just asks you for the roots, all you got to do is find those values. Right here again, what's the value? We see it at negative 1, negative 2. By the way, if you don't see values written down, we're going to assume it's by 1. So this is at negative 2. Why don't you take a minute here now? Let's see which equation has no roots. Which equation has double roots? Okay. Well, there's roots clearly here, but no double roots. There's no roots here, right? It's below the x-axis, opening down, so no roots right there. We see right here, just touching the x-axis, so that's a double root. We call it a double root when it's only one root, because you'll find out that actually stands for that. Well, there's a reason we call it a double root. Let's just say it that way. So this is a double root, and right here we just have two regular roots. Awesome. Let's look at this right here. Disc golf, Rex. is making a throw from a short distance. The equation h equals negative 16t squared plus 15t plus 6 models the disk's height h in feet t seconds after the disk is released. Use a graph to estimate how long the disk is in the air. Okay, so if h is the disk height, t is the seconds. Okay, so that's kind of like h is our y, t is our x. So let's look right here. We're going to use Desmos to help us out. That's negative 16t squared. Negative 16t squared. Sorry, I'm just going back and forth. Oh, not to there, though. And that would be what? Plus 15t plus 6. Plus 15t plus 6. Plus 15t plus 6. I was putting t, but we're gonna transpose this for x for Desmos purposes because it's just built for x. So for delete x. There we go. That makes a little bit better of a graph. So we notice, by the way, this graph goes into negative x territory, but we can't have negative time, right? Because that's really our x is our t here. But what we have here is we see the graph. It's only flying in the air for about 1 to 2 seconds. Okay? So it starts at 0 right here, and it flies for about, I don't know. All right, so as we're looking at this, just looking in between, we see it's about, I don't know, looks almost like, let's see if this is 1, 2, 3, 4, 5. It looks like what, about 1.22 seconds, right? About 1.2 seconds. So I'm going to write down 1.2 seconds is the graph, and then if I use the technology, so I actually click on it, oh, we're not far away, it's 1.24. It's exactly 1.24 seconds. And how does our solution compare to our estimate? Well, our solution is exact, right? The solution is exact. So when we can find exact values here, it's better than an estimate, right? An estimate's always going to have some error in it. That's all we're getting at there. So if we go back to your paper, here's what I have filled in. We guessed about 1.2. It's really 1.24, and the solution is exact. It's more precise. That's it for today, guys. Hopefully the homework's going to breeze right by for you. With that said, peace out.